Good. So let's see here. Last day. Last day we finished that graphing question, right? Kind of tricky. There's lots of components. And then we started on exponential functions. So chatty, must be Friday. All right, so we started chapter 4, and we were actually supposed to finish chapter 4 this week. We'll see, we'll try our best, right? But we might take it into next week a little bit. I want to try to get through it today though, so hang tight. What's tricky though is that it's actually really important. There's not going to be a whole lot for me to tell you about. It's going to be practicing and using the rules that we establish, right? So I'm going to tell you the rules, and then we need to practice working with these rules, right? So it's a big chapter in that sense that it's really important, right? To work with exponents and logs, but as far as how much we're going to do together, it's not going to be a whole lot because there isn't, you know, a whole lot. But so last day we started talking about exponential functions, and an exponential function is just anything a to the power of x, right? Where a is the base and x is the power. And we talked about, you know, what do these things look like, right? We could have growth or we could have decay. And as a fact, we said that no matter what the base is, it's always going to pass through 0, 1, right? So it's always, when x is 0, the value is always going to be 1. And then we used our calculator to figure out how do we calculate these things, right? And that's just a matter of getting to know your calculator, right? Knowing how to use it. And then we looked at some graphs. We're not going to have to do this right on a test, but it's good to kind of figure out the behavior, right? So if we're given a point, we can figure out if it's growth or decay, that kind of thing. And then we introduced probably the only applied thing that we'll be doing, right, in this whole course. There's lots of things that we could be doing, but the applied stuff is going to be in exponents and logs, right? Because otherwise there's no motivation behind it. One of those is compound interest, right? So if you make a deposit at the bank, then you make interest on that, right? How that interest behaves is if you've got compound interest, right, then usually the bank does twice a year, right? Twice a year it checks in, sees how much interest you have made, and compresses that or compounds that with your initial investment. And then from that point forward, you're making interest on your initial investment as well as the interest that you've made, right? And then the next 6 months or so go by, the bank does the same thing. They check in, how much interest have you made, compresses it or compounds it, and then you make interest on that, right? So that's compound interest. So you're making more and more interest because you're getting interest on a larger and larger amount. Yeah. We talked about some common n's, some compounding rates, right? So if it says annually or once a year, then n is 1. Semi-annually is twice a year, right? Monthly is 12 times per year. Weekly is 52 times per year. Daily, we say, is 365. And then we did some problems, right? We had to look at 58, and we said, okay, I'm going to invest $2,500 at a rate of 2.5% per year, and then find the value of the investment after the given number of years. So we did A. And you know what? Did that one feel okay? It's going to come back up in the next section anyways. So how about we just kind of sit on that for a little bit, right? And then we'll keep working on those types of problems as well. So just as review, right, we had compound interest following this formula. And so we calculated compound interest. And one important thing is that the R that we use has to be the decimal form, right? Usually we say, okay, you get interest at 2%, right? But that's 0.02 when we do our calculations, right? So we always have to divide by 100. And so as a decimal for your R, which you've probably already got a note about. Okay. But the formula that we use, right, is P, which is the initial investment or the principal amount, times 1 plus, and then the rate as a decimal over n, how many times per year we're compounding, to the power of n times t. Now it's really small on here, right? But it's to the power of n, the number of compoundings, times t, which is however many years we let it sit there for. So if we keep going, where's my side notes? From section 4.1, let's do one of these values here, or one of these problems. Let's do, they're the same, right? But let's do 62. The present value of a sum of money is the amount that must be invested now at a given rate of interest to produce a desired sum at a later date. Right? So this formula that we use, A of t, that's the amount that we need later after t years, right? And so here we can make a note that A of t is the amount that we get after t years. That's what it says in the summary, right? But sometimes it's just helpful if we write it down twice, right? Or write it down ourselves. So P is the principal amount, but P can also be thought of as the present value, right? The present value of this investment is your P. So that might be helpful to know, right? You want to have, $10,000 to buy a car in 5 years from now, and the bank says, fine, we'll give you an interest rate of, I don't know, interest rates aren't very good right now, 1.2%, right? And then you can say, okay, well, how much do I need to invest now for it to let it sit till it grows till 10,000? Yeah.
So does that mean that the principal amount and the present value are the same thing?
Yeah.
Okay.
Mm-hmm. So it's just different terminology. Right, so I'll just say or P is the present value. So if we want to find the present value in question 62 of $100,000, if interest is paid at a rate of 8% per year, compounded monthly for 5 years. So if we write down our formula, right, we know in general A of t is P times 1 plus R over n to the power of n times t. in our question, we're given that A of t, so after 5 years, we're going to have 100,000. The interest rate is 8%, so I'm just going to write 0.08 right away, just to remind myself that I have to use decimals. And the compounding, it's compounding monthly, so my n, the number of compoundings per year, is going to be 12. And then t is the time in years, which must be 5. Okay. So now, starting with the empty shell for the formula again, 1 plus r over n and t, I can plug these values in and then solve for p. So I get 100,000 is p. I'll clean up this p here. P times 1 plus 0.08 divided by 12 to the power of 12 times 5. So we're back to BEDMAS, right? Making sure that you do the 0.08 divided by 12, then add it to 1, then to the power of 12 times 5, and then divide it over. So I get 0.08 divided by 12 plus 1. So I get P times 1.00666 repeating, and then 12 times 5 to the power of 60 is 100,000. Plus 1. So raise 1.006 repeating, making sure you keep all your decimal places, right? Because whenever we're dealing with money, right, you don't want to be rounding. You want to keep all your decimal places until the very end. You can play around with it, right, and see what would happen if you rounded here. You would get a very different value. Right? So it makes a huge difference. So now we want to go to the power of 60 and just showing all my steps here. If you wanted to skip to the end, that's fine. I just want them to be here when you look back at the notes. So I get P times 1.489845708. Solving for P, I divide both sides by 1.4898, blah, 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 blah. So I get P, jumping around on me, is 100,000 divided by 1.489845708. Keeping that in your calculator, I do 100,000 divided by the previous answer. P is 67,121.04444.
I got 0.4446. I got 67,147.
Okay. What I think, let me just do this calculation quickly here. 0.08 divided by 12 plus 1 to the power of 60, and then 100,000, 1, 2, 3, 4, 5, divided by the previous answer. No, I get the same answer. Okay, so I think what's going on here is my calculator saved more than this, right? This is how many it's able to show. So if we're only going to here and putting that in, then it's going to be slightly different. I think that's what happened here. And then to get the other answer, So that's why I keep everything in my calculator, and whenever I can, I just kind of, because on my calculator, I don't know, it depends on your calculator, right? But usually there's a previous answer button.
No,
right?
the value of, what is it? Does it say previous?
Yeah, that one. So if you go second answer, then you can go, so then you can calculate this guy, and then you can go 100,000 divided by that previous answer. I use that a lot, right? Yeah. Yeah, so it depends on your calculator, how it works, but we can have a look. There's even ways to store values. I just started using this calculator for another course, so I'm not really familiar with it. But I see there's a store function, an STO function. So there usually is. And then what you do is you can just put values into slots. You have to remember where you put them. And then you can do a recall. And usually YouTube's pretty good. You can just Google your calculator, how to store values in my calculator. You just tell it what your calculator is. So I still have to do that on mine. Hasn't been essential quite yet, but for things like this where it actually matters what our decimals are, might make a difference. Did you get yours figured out? No?
Because I got different value over there. 1.489
Whoops.
is the same.
Yeah.
But after that, I got different.
And did you keep 0.08 divided by 12?
I just start calculating after that.
So here, this 6 is repeating though, so that's going to make a difference, right? So you want to start all the way from here, 0.08 divided by 12 plus 1 to the power of 60. That's going to get you this one. And then 100,000 divided by this one, but it keeps going. Right? So yeah, that's the tricky part when you're dealing with money. Usually, I mean, we do stuff like this in Excel. Excel just keeps track of all your numbers, right? So we probably wouldn't do these things by hand, right? Anyways, but it's good for like personal finances and just kind of knowing how it works, right? Because it's actually not that complicated once you've seen a few. Because this is money, I want to round to 2 decimal places, right? We can only have 2 decimal places for our pennies. So 0.04. Okay. So one thing I will say here is make sure you keep all decimals in your calculator. All right. So what does that mean? That means that in order to have $100,000 in 5 years, if I can get my hands on a rate of 8% per year, not likely these days, used to happen, right? Long time ago. Now our rates are more like 1%, that kind of deal. Not as good, right? But at 8%, compounding monthly for 5 years, we would only have to invest $67,121.04. And then it would just sit there, and after 5 years, we would have 100,000. It's pretty good. Right? If I ask you this, how much interest have we made? Right? How much did we make in interest? If I ended up at 100,000, but I started at 67,121, I haven't been making additional contributions, right? Everything between here and here is interest. Chloe's got it.
32,179.
Cha-ching.
That's so much better than my interest rate.
Yeah. Yeah. We only get those well, that's a good lending rate. If we're borrowing money, 8% is pretty good. Works the other way too, right? If we buy a house, we end up paying a lot in interest, right? Then it's not so fun. So we have paid, or sorry, we have not paid, we've gotten 100,000. This is me adding to the question, but I think it's pretty useful. 67,121.04, which is equal to 32,878. How many pennies? Here, I got it. 1, 2, 3 divided by that guy. 96. Good. In interest. I guess I shouldn't say gotten. We have earned. That's more proper. Although we didn't do anything. We just gave the bank our money. After 5 years, they give us 32,000. It's pretty good. So, pretty fun to be able to do those calculations, I think. And we'll look more at some more kind of investing problems. Any questions about this one though? No? So this type of stuff, if you like this type of stuff, you should take business math. It's really fun. Well, to me, it's really fun. And it's basically just all stuff like this, right? You invest this much, how much do you get at the end, right? There's different, you know, complications that we can add, right? What if I, you know, invest 67,000 and then in 2 years I invest another 10,000? They're both making interest. After 5 years, how much have I made, right? So we can add kind of layers, but at the end of the day, this is all we're doing in business math. So pretty fun. If you need an extra credit or something, right? So, any questions about that one? Let's go on to 4.2. So section 4.2, put it on a fresh page here. 4.2 is about the natural exponential function. So the natural, exponential function. Okay. The natural exponential function is actually, it's the e to the x that you've probably seen at some point, right? So the first bit of the handout just talks about the number e, and we don't really need to know any of this, right? What might be useful is that e is approximately 2.71828. There's a song, I can't remember how it goes, but e is a number 2.71828, and then it just keeps going and it lists a bunch of the numbers. But anyways, that doesn't matter, right? Roughly 2.7. Okay, so it is just a number, but just like pi, it keeps going forever and ever, right? And so, so we can't really pinpoint it, right? But all calculators are going to have, any scientific calculator is going to have an e to the x button, right? And so if you do e to the power of 1, e to the power of 1, you should get 2.718281828. Yeah? Good. So it keeps going. Can only show that many though. Right? So that's the button that we're going to use for e to the power of something. And I can't remember if I copied this, so I'll do it again. So the natural exponential function, right? Remember the exponential or an exponential function is a to the power of x, right? The natural exponential function is e to the power of x, right? And so that's what your calculator does. And depending on your calculator, again, right, mine just puts a little e and then I have to raise it to the power of something. Some calculators will do e and then want the number in the power in brackets, right? So again, make sure that, and we'll do some exercises so we can figure out how your calculator works. So the base is e, and this one is the most kind of frequently occurring exponential function that we actually end up calling it the exponential function, right? And so, you know, we can have 2 to the power of x or 3 to the power of x, but at the end of the day, if I say, okay, we have an exponential function, what I mean is e to the power of x, right? And so, right, so it's often referred to as the exponential function. So let's just have a peek and make sure that we know how to use our calculator for this stuff. If you look at the first chunk of exercises, and just like before, we'll just do a couple of these. We don't need to do all of them, but if we do question 4, for example, we're told that h of x is e to the negative 3x. And then we want to figure out what h of 1 over 3 is. So h of 1 over 3. So now I'm replacing x's with 1 over 3. So I get e to the negative 3 times 1 over 3. That's right. So I get e to the negative 1. So let's do that on our calculator. So find your e button to the power of negative 1. I do squiggly equals whenever I'm going to write down a decimal from my calculator that's not exact. And so it means approximately equal. And so we've got 0.3678794412. So make sure that when you use your calculator, that you get the same thing, right? When you do e to the negative 1. Let's do another one. H of 1.5 is going to be e to the negative 3 times 1.5, right? 3 times 1.5 is 4.5. So I get e to the negative 4.5. And then when I do that on my calculator, e to the negative 4.5, I get 0.011108999654. What if we do, well, we're so close, we may as well do the rest of them. H of negative 1 is going to be e to the negative 3 times negative 1. So now I'm going to get a positive value, right? Because I get e to the power of positive 3. E to the power of 3. Now I get 20.08553692. What about h of negative pi? Okay. So h of negative pi, I'll put it on a new page, is e to the negative 3 times negative pi. No, we want to use all of pi, right? So there's a pi button on your calculator. And so we want to use, so we get e, so -3 times negative pi. I know it's going to be positive, right? So I get e to the power of 3 pi. So first you're going to find 3 times pi, or usually this is how I do it. I figure out what my power is, and then I use that previous answer button to do e to the power of that. So I get 3 times pi, 9.424777961. No. Should be close to 9 though, because it's 3 times 3 essentially. Oh, are you doing e to? I only did 3 pi.
Oh.
So then if I do e to the power of that, I'm like, wait, I know what's going on here. E to the power of the previous answer, I get 12,391.64781. Good.
I was like, I'm really
No, that's only confirming the 3 pi. Cool. So we're feeling pretty good. Able to use the e to the x button. That's good. All right. Then let's have a look at some of the things that we can do. Oh yeah, and it just illustrates here, right? Because we know that e is 2.718, right? If we think about it that way, what we can do is we can look at, okay, well, e to the power, or sorry, 2 to the power of x looks like this, and then 3 to the power of x looks like this. So it makes sense that 2.718 to the power of x is somewhere in between those two, right? And it's going to be closer to the 3, right? So it is just a number in there and it behaves the exact same way as the others. So we can just talk about, I put this example on here just so that we can have a look. Because this is a pretty common use of the exponential function. So when things grow exponentially, right, then it starts slow and it doesn't grow very fast, but then as soon as, you know, let's say enough people get coronavirus, then the spread of coronavirus just, it'll be exponential, right? And so here, I wasn't even thinking. How apropos. So an infectious disease begins to spread in a small city of population 10,000. So if we think about, okay, so we've got this infection and it's going to start spreading, you know, one person has it, whoever they live with gets it, their neighbors get it, and then the neighbors go to work, and then all of a sudden, right, everyone has it eventually. In a small city of a population of 10,000, right, once close to 10,000 people have it, kind of, that's it, right? And everyone has it and everyone just has to get better, right? And so after T days, the number of people who have succumbed to the virus is modeled by this function. And this is a pretty common kind of spread function. So we've got our 10,000 people, and you don't have to know, but I'm just telling you where these things came from. And so the 10,000 is kind of your cap, right? That's the maximum number of people that can get infected, right? And then we've got this kind of secret function down here where we have 5 plus 1,245 e to the negative 0.97t. Okay? And so we don't need to know how this part came about, right? But as t gets larger and larger and larger, right? So as more time goes on, right, the more and more people are going to be infected. So we can answer questions like, how many infected people are there initially, right? So this is the number of people infected. And if time is 0, right, all I need to do is evaluate this thing at 0. The only variable I have in here is the t. So what we can do, let's see here. How much of this thing did I copy over? Oh, wow. Okay. I'll put it in our notes so I don't, you've got it in front of you, so I don't need to write it out a bunch of times. Okay. But I will make some notes on here. V of t is the number of people with the virus. Number of people with the virus.
The whole equation is going to be like ideal situation for even spread.
Well, it's going to be exponential growth, but actually that's being taken care of by doing e to the negative 0.97 t. Yeah, so that kind of takeoff growth is captured by that guy.
Okay.
So it's just going to be a matter of plugging in values and figuring out what it is, because that's already handled. Nice. So, I mean, we have it here. All we would do, right, and we'll check on our calculator, is we would plug in t equals 0 to figure out how many people were initially infected, right? And so this goes to 0, so we have e to the power of 0. Anything to the power of 0 is 1, but also, just thinking back to that graph of our exponential functions, right? It doesn't matter what the base is. When x is 0, y is always 1, right? We saw that. And so that's the link, right? But anything to the power of 0 is just 1. So here we've got 1. So we've got 5 plus 1,245 times 1. 10,000 divided by that. So I get 10,000 divided by 1,250, and we'll just double check their work. It is just 8. So to start with, right, at time 0, 8 people have this disease, right, and then they spread it. So now we want to find the number of infected people after 1 day, 2 days, and 5 days, right? And we'll see that it starts off slow, right, spreading, and then as time goes on, right, it's going to spread faster and faster and faster. So they've done the calculations for us, right? We can confirm them, but so after 1 day, right, from 8 to 21, and then from the next day, we will go from 21 to 54, right? And then 3 days later, we go from 54 to 678, right? And so we've captured that kind of exponential growth. It says from the graph in figure 4, we'll just make our own graph, right, in Desmos. If we graph this thing, right, we can do 10,000, 1, 2, 3, good, divided by 5 plus 1,245. And then for e to the power of something, you're going to go into the functions, right? So functions, and then I think it's in the miscellaneous. Yeah, so over here in the misc, you've got exp. Okay. So exp, and then what it wants is in brackets what the power is, right? And that's pretty common if we use Excel or if we use some other software. It does exp and then in brackets whatever the power is. And we want negative 0.97x and bracket, where x is our time. So what we see here, right, we're not really concerned with what happened at negative time that didn't happen, right? The function still exists, but here we said we started at 8 people infected at time 0, and then we moved to time 1, somewhere around here. Can't see. 20-ish. Can't land on it. Right. And so we've got, if we zoom out, it doesn't take very long at all. Here, this is to 50, so it's kind of hard to see, but it doesn't take very long to reach 200 people infected. And so it just kind of takes off that way. Oh. Cool. Let's zoom out to 2,000 people. Up, 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 up. Right. So what happens? I guess I said 10,000, but that's the population. Not everyone's going to get sick. And so it's going to plateau at 2,000. So how do we figure out that behavior, right? That's as t gets larger and larger and larger, right? And so if we figure out, so here, to see what the end behavior is, end behavior is, right, we let t go to positive infinity, right? We let t go to a very, very large number. Okay. What we need to know from our function, right, v of t, here we go. V of t is 10,000 divided by 5 plus 1, 2, 4, 5 e to the negative 0.97 t. Let t go to positive infinity. Right. So we've got negative 0.97 times a very, very large number, right? And then e to the power of that. So what I want you to try is figure out how e to the x behaves as we have a negative large number. And so here, e to the negative, and I just think of it as infinity, right? I'll put kind of air quotes around it. We can't actually do that. Infinity is not a number, right? It's a concept, it's an idea. And so e to the negative infinity, right? What's that going to look like? Well, we can try just huge values of the power, right? And so if we do e to the power of negative, let's try something like 1, 2, 3, 4, 5, 6, 7. I think I did 8 or 7 zeros after my 1. Just going for a huge number. Oh, it was too many. It didn't like it. E to the power of negative. How about if I go to 100,000? Still too big. It can't handle it. E to the negative 10,000. Still too big. E to the negative 1,000. E to the negative 100. I'm resorting to Desmos. EXP to the negative x. It's doing something weird. But if we zoom in, right, around 0, we see that we get this graph. Right? E to the negative x is actually 1 over e to the x, right? Which means that we have a fractional base. So we're going to have this decay, right? E to the negative x is decaying as x increases, right? So it's going to go to 0. So what happens is in Desmos, we see that the graph of e to the negative x in general looks like this.
So could you kind of find out after how many days it would plateau after by just plugging in e to the negative days? Or would you need to do the whole
Yeah.
equation?
You could figure out the value that it plateaus at and then work backwards, right? Kind of set something a little bit less than that and then figure out how many days it takes to get there. And we can look at one like that. So e to the negative x is going to go to 0, right? Or approaches 0, right? Or at least a very, very small number. So e to the negative x approaches 0. Oops. As x goes to positive infinity, right? So if we look at our v of t is 10,000 divided by 5 plus 1245 e to the negative 0.97 t. What we're saying is that this whole chunk is going to go, so e to the negative 0.97 t is going to approach 0 as t goes to infinity. Which means if this whole thing is going to 0, then the 1245 falls away, but we've got this 5 still. Right? And we're not concerned with how that 5 got there. We're not going to do that, right? I would just give you the function and we have to know how to use it, right? And so what we're left with is v of t is going to be 10,000 divided by 5 plus, and I'll do kind of 0 or at least a very, 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 very small number. And so as t goes to infinity, so then we get 10,000 divided by 5, which is that 2,000. The number of people infected will plateau, right? So just kind of level off. Plateau, and I'll say slash level off, whichever makes more sense to you, at 2,000 people infected.
Is that the total number of people infected or the new amount of people being infected today?
It's the total number of people infected. Yeah, so we keep adding to the number But like I said, some people, you know, won't get it, that kind of thing.
Yeah.
Right? And so that's what the 5 is doing. So if you've got a small number, right, then the plateau is going to be a lot higher. So thinking about a problem, right, how long is it going to take for us to get to that number, right? How long until we reach about 2000? So if we remember our graph, right, it kind of approaches 2000, looks like a horizontal asymptote, right? But if we try to get to a value that's a little bit less than that, then we can figure out approximately how long it took to get there, right? So if we want to know approximately how long it will take to reach 2,000 people infected, right? And I'll put in brackets here. This looks like a horizontal asymptote to me. So what we can do is we can do calculations on, let's say, 1,900 people infected, right? At that point, we're kind of close enough. We can figure out how long it will take. Oh, we're gonna need logs to solve this problem. It's just going down that road. Oh, what a fun twist. I wonder why they didn't do that. We don't have logs yet. But maybe it's a good segue into logs, why we need them, right? So here, I'll finish what I was saying, because this is a problem that we will be able to solve in just a little bit. So here we go. So we can figure out how long it will take for 1,000, even 950 or something close, right? A value close to 2,000. How long it will take for 1,950 people to get infected. Wasn't even paying attention. So what we want to do, right, is we want V of t, we're going to force it to be 1,950, which is 10,000 divided by 5 plus 1245 e to the negative 0.97. Oops, keep forgetting to put the 7. 0.97 t. Huh? Do you see the problem? What I just kind of railroaded through in my mind earlier? We can bring this guy over here. We can start to solve this problem, right? But you'll see what I mean in a bit here. So if we multiply both sides by 5 plus 1245 e to the negative 0.97 t, right, we get 1950 times 5 plus 1245 e to the negative 0.97 t is 10,000. And just by our usual methods, right, I try to isolate my x or whatever I'm solving for, right? So now I'm going to chip away and try to get t on its own. Right? And so now I've got 10,000. I can divide that by 1950. So I get 5 plus 1245 e to the negative 0.97 t is 10,000 divided by 1950. 10,000 divided by 1950. It's not a nice number, so I'm actually just going to keep it as a decimal or as a fraction, right? Because I don't want to be rounding my decimals.
Like 960, 1960 or 1970, it's matter or it doesn't matter?
No, just something close to 2000. Because what happens is, if we have a look at the red graph, is the graph of this curve. Here. What happens is, it'll approach 2000, but we don't really know if it's going to get to 2000, right? It might keep going and have this horizontal asymptote here. So that's why I don't want to use 2000 exactly. Might work, right? But we don't know, and I don't want to risk it. So that's why I put it a little bit lower so that I know I can solve for it. Right? So that's why I picked 1950 down here. Is this the same amount of time as here? Close enough. Right? So it'll be a little bit off, but pick a value close to that boundary. So I can still pick away at this, right? I can subtract 5 from both sides, just following the rules of algebra here. So I get 1245 e to the negative 0.97t is 10,000 divided by 1950 minus 5. So this is all one number. I can divide that by 1245, right? Remember, we're picking away until we get t on its own. So I get e to the, I'll scoot it over a bit to make myself some more room here. E to the negative 0.97t is 10,000 over 1950 minus 5 divided by 1245. Here's the problem, right? We can't solve for this t. We don't have those methods yet, but that's where logs come in, okay? And so we can't solve for this yet. We can't solve for t because, or you know what, I'll say for t yet. Because it is in the power. Let me see here. We need logs to be able to solve for values in the power. But wasn't this a nice opportunity to see? So we will come back and we will solve this, but we'll finish section 4.2 first before we get into 4.3. Oh. But nice work. Okay. So there's a couple of different functions and it just asks you to work through them, right? But I want to go to continuously compounded interest, kind of leave you on this cliffhanger for a little bit, right? Till we can get there. So on the next page, if you have a look, we talk about continuously compounded interest. And continuously compounded interest is this really fun concept where the bank isn't looking at how much interest you've made every month or every week or every day. What it's doing is it's considering how much interest you've made at every moment, right? So continuously. So it's always being compounded, which is really hard to wrap your head around, right? It's not even every minute. It's not even every second. It's every moment, right, that exists. So what we think, just kind of in our minds, is, well, if it's continuously compounding, right, if it's smashing on all that interest that I've made every single moment, I must be making tons of money, right? But what happens is, because the rate gets slashed into every single moment, right, it's not going to make a huge difference. And so, but we can calculate compound interest by a similar formula that we were using, right, where A of t is still the amount after t years, right, the amount of money that we'll have after 2 years. P is the principal, right, so the amount that we initially invested. R, again, is the interest rate per year as a decimal, and t is the number of years. And then we can calculate it. A of t is P times e to the RT, so it's a nicer formula. I'm just going to steal this guy. I'll make a note here from the one we were just talking about. We will come back to this. So R, let's just make a note here, oops, is still as a decimal. That's going to be important. And T has to be in years. So if I tell you, oh, you invest it for 7 months, right? 7 is 7/12 of a year. I don't think we're going to get into that kind of detail here, but just as a heads up, T has to be in years. So now we can use these formulas to solve some problems. Which one did I want to do? Let's do 35. Only because I want you to see the difference between the different compounding frequencies, right? Annually, semi-annually, quarterly, and continuously, right? So for annually, semi-annually, and quarterly, we use that previous formula that we had, and then continuously, we use the new formula that we have. So let's do number 35. Oops. I need to copy it, that's why I'm here. So here, just like I promised, we get to do some review of those ones where we ended last day. So I'll let you guys plug away at it, and then we can check in and make sure that we have the same answers.
So we're not using the compounding?
Not until part D. So we want to see just how the compounding frequency affects the amount that we have at the end of the day, or at the end of 10 years, I guess.
How to take the end date?
Pardon?
How to take the end date? Like, oh, okay. And so
Because we want to do annually, and then quarterly is going to be 4 times per year. Okay. Looking at these values, right? After 10 years, does it matter what our compounding rate is? A little bit, but not enough for us to care about, right? So the values are going to be different, but in the grand scheme of things, it actually doesn't matter how frequently we're compounding, right? Whether it's annually, semi-annually, or continuously even, right? Because the amount that we end up with is around 769-ish, right? Regardless, 768.05, 769.22, 769.82, right? Very similar. And then even when we're compounding continuously, right? Every single moment, we end up at 770.42. right? Because we kept the rate the same, the time the same, and the initial investment the same, right? So the only thing that's changing here is our compounding frequency, right? And so kind of the take-home message is, it doesn't really matter what compounding frequency you have, right? It's the rate that's going to matter. And then how they slice it and dice it, to you at the end of the day, is not going to make a difference. If I said, oh, here's $768, and you said, wait, 10 years later, I thought you said you were going to give me $770. Not really that big of a deal. Right. So it doesn't matter. It matters in the sense that we get slightly different numbers. Right. But for us, when we go to the bank and the compounding frequency isn't going to change much. So, and then in question 37, kind of an interesting process, right? Because what you're going to do is it asks you which of the given interest rates and compounding periods, right? So now we've got a combination of a different interest rate with a different compounding period would provide the best investment, right? And so this might be useful, right? If you're going to the bank and they're saying, hey, here's some options for where you can put your money, right? 2.5% per year compounded semi-annually, right? Or 2.25% per year compounded monthly, or 2% per year compounded continuously. Right? We've got different rates, but also different compounding frequency. And so what you can do is you can just say, well, what if for each of these scenarios to compare them, right? What if I just say, oh, I'm going to invest $100, right, in each of these scenarios, right? And maybe let's just look at how much am I going to have after a year, right? So to solve this problem, we can pick any value of P and T, and compare the values of A of T. And compare the values of A of T. Okay. So if I let so I'm sitting and I've got $100, and let's just do T equals 1, right? How much am I going to have of this $100 after a year? You could let it be 10 years. It doesn't really matter, because you're looking for the same time frame for all of these problems, right? And the same initial amount. And so it actually doesn't matter. So part A, we've got a rate, R is 0.025. And N is compounded semi-annually, so N is 2. So we've got A of T is P times 1 plus R over N to the power of N times T. So in this scenario, I invest my $100 and I get times 1 plus 0.025 divided by 2 times 2, or to the power of 2 times 1 year. So I get 0.025 divided by 2. Remember, you always start with this guy, simplify that, then add it to 1, and then take the power. So plus 1 to the power of 2 times 100 I would have 102.515625, or in money, 102.52. Cha-ching. I made $2.52 in interest, right, in that scenario. So let's look at part B to compare. Now I've got 2.25% per year compounded monthly. So now R is I'll do 0.025, and N is monthly, so 12. Yeah, thank you. So I get A of t is P times 1 plus R over N to the power of NT. Still my $100 bill plus 0.0225 over 12. Oh. Times 12, or to the power of 12 times 1. 0.0225 divided by 12 plus 1 to the power of 12 times 6, or sorry, not 600, 600 times 100. I get 102.27334888. In money, $102.27. Between these two that we just calculated, I guess I would rather have the first one over the second one, right? Won't really matter, but I would pick that one if I had a choice, right? So now let's compare it to 2% compounded continuously. So now, part C, R is 0.02 and N is continuously. So now we use that continuously compounded formula. So A of t is PE to the RT. 100 times E to the power of 0.02 times 1. 0.02 E to the power of 0.02 times 1 times 100. I get 102.020134. In dollars, 102.02. If we're investing $100, right, either way, right, it doesn't really matter. 102.02, 102.27, or 102.52. I'd probably pick this one, right? If I was investing $1 million though, then I start to care a little bit, right? Because now we're talking about kind of $25,000 versus $22,000, right? And so it kind of starts to matter a little bit more, right? But the differences stay the same, right? It's just kind of what scale we're working at. Right? And so for $100, we're given a choice, we would pick this one, but it stays the same regardless of how much you're investing. Right? So that's how you would pick the best interest rate. Right? And so you can use that in real life. Right? You have to make investments. Or you can just hire someone to do it for you. Works too. But it's nice to know kind of what they're doing. It's nothing really crazy. Any questions about those investing problems?
I just want to know how you get the value of R is equals to 0.025 and 0.0.
Because here, right, we said a 2.5% per year. So this says that R is, oops, 2.5%, which is 0.025. Right? Because 2.5, 2.25, 2.25%, which is 0.0225. It. Is that good? Any other questions? No? Okay, then let's get into 4.3. Logarithmic functions. So we said that, okay, we're going to need logs, right? So here we go. Let's introduce logs. Started on a fresh page here. 4.3, logarithmic functions. Logarithmic functions. So logs are just the inverse of an exponential function. Right? So the inverse, right, is the one that kind of undoes the original function. And so logs, right, or logarithms if you prefer, but logarithms, you can just call them logs. Logs are the inverse of an exponential function. So we can bring in that, oh, not 4.3, 4.3 is there. We can bring in the definition and we can talk about it. So if we let a be a positive number not equal to 1, the logarithmic function with base a, remember, so a to the power of x we said had a base a, right? And so that's how it's going to be related to an exponential function, denoted by log and then subscript a. Log base a is how we read that. Log base a of x is equal to y means the same thing as a to the power of y is equal to x. So the relationship here is that this a to the power of y equals x, right? And that can be a little bit confusing, right? And so what we do is we can write it out. Log base a of x equals y. Okay. This says that, okay, we take this a to the power of y equals x. Confusing, right? Maybe I'll put all those in color coded. So that's the relationship. It's a little bit confusing, right? Most calculators are going to have a log button, right? Mine even has a log base, and I can just tell it what base I want so that we don't have to work so much with these logs. Because if we have a look at some of the exercises without the calculator, what we can do is there. from these, right, what we want to do is we want to figure out, okay, so here I've got log base 2. Oh, it captured my kind of drawing there. If we're evaluating these things. Now, we're not going to do these by hand, right? I'm just going to show you how we would do it by hand. You're going to use your calculator. And if the calculator that you have doesn't do it, there is a trick that I'll show you in a little bit. So don't worry, we won't have to do these by hand. But how we would do it is, okay, so I've got log base 2 of 2. Right? So translating this to this and this, what I want to do is to figure out what it's equal to, I want to think about 2 to the power of what equals 2. 2 to the power of 1 equals 2. Right? Even something simple like that is kind of hard to think about. Right? And so if we start talking about 25a, right, we've got log base 2 of 2. We want to ask ourselves, what to the power, or sorry, 2 to the power of what? Yeah. 2 to the power of what equals 2. Right. What we can say is log base 2 of 2 is 2 to the power of 1 actually, that's not true. Is 1, since 2 to the power of 1 is 2. That's what I wanted to say. I'll put a big red note next to all these calculations, right? We do these on our calculator. Right, so they're not something that you need to do. I'm just showing you how it works. What if we go to part B, log base 5 of 1? Well, 5 to the power of what equals 1? Well, 5 to the power of 0 is 1, right? Anything to the power of 0 is 1. And so that's going to be, oh, I almost did it again, is 0. Since 5 to the power of 0 equals 1. Part C, even trickier, sort of. Log base 6 of 6 to the 5. Log base 6 of 6 to the 5. So now we want to do 6 to the power of what equals 6 to the 5? Well, then must just be 5, right? Since 6 to the power of 5 equals 6 to the power of 5. What about one that's not quite so obvious? What if we did 26b? 26b, log base 4 of 64. So log base 4 of 64. So now we want to figure out 4 to the power of what equals 64. So we're just going to try a few values, right? 4 to the power of 2 is 16. 4 to the power of 3 is 64. So the answer, right, is going to be 3, since 4 to the power of 3 is 64.
So when we put log into the calculator, what is the base it automatically?
So it depends on your calculator. If it just says log, it'll be base 10. Okay. But like this calculator has, I can just tell it what base I want, right? But, and I almost want to skip straight to it. It's not until section 4.4, but do you want to know the trick now in case you have to use your calculator? And so a scientific calculator will have a log of x button. Log of x button. This is log base 10 of x. So you feed it whatever x you want. Log base 10 is called the common log. So log base 10 is called the common log. So if it's just written and is written just as log. So we kind of dissolve the base 10. If we kind of fast forward a little bit, the other common base that we're going to work in is log base e. So that's called the natural log. So another, you hate to say common because we've got the common log, right? In fact, I'm going to go so far as to say that the most popular base, for logs is e, right? And log base e is written as ln. And it's called the natural log. And any scientific calculator will have that ln button. So any scientific calculator will have an ln button. Oops. So at the very least, if you can't specify the base on your calculator, you should have a log button and an ln button, right? Log base 10 and log base e. But what's interesting is the common log, so log base 10 is used for things like sound waves, right? So as soon as you've got kind of sound, kind of intensity, right, then we use log base 10. So engineering, kind of log base 10. Computer science, they use a lot of log base 2, right, because everything's binary. And so they use a lot of log base 2. Everyone else in the world's like, log base 2, no thanks, right? And so that's why we don't have log base 2 on here. And then every other science uses log base e, right? For, you know, biology, chemistry, chemistry, sometimes they'll use log base 10, but most things that we're doing are going to be log base e, right? In fact, I'm bad because I did my math, stats, and we only use the natural log. So I'll write ln, but sometimes I say log because that's the only log that I care about in my line of work, right? I try to be good and say the natural log, right? But sometimes I'll write ln and say log, right? So just be aware, right? And usually I'll put a little side note here because it might be hard to recognize. I write ln like that, right? So it kind of ends up looking like a scribble, but just so that you know what you're looking at when I write that. Huh? So I write kind of a cursive ln. So some calculators will have a log and then an empty box button. Right. Then you can just calculate log base whatever, right? So in that case, we can just calculate the log of any base, right? Because we can just tell it, oh, I want log base 3 of 5, right? So if I do that on mine here, log base 3 of 5 is 1.464973521, for example. Right? So if you have this button, you're in luck. You don't have to pay attention for the next bit, right? I just want to show you, in case you don't have that button, then I'm skipping ahead to section 4.4, but I think it's worthwhile showing you now how to do the change of base formula. And so if your calculator does not have a log empty space button, we can use the following. And this is from section from 4.4 notes, because I am skipping ahead a little bit here. The change of base formula, which means that I can rewrite log base b of x as log base a of x over log base a of b, which means that I can pick a convenient value of a here, and for me, that's always going to be log base e. Okay? So I will always use a equals e. So what that means is that I can rewrite log base b of x is ln of x over ln of b. In fact, I'll write my so now we can evaluate crazy hard log problems just using the ln button. Right? So now, if I want to do something crazy like log base 14 of 3, I don't even, should work. What do? I take the natural log of 3 over the natural log of 14. Natural log of 3. I get 1.098612289 divided by the natural log of 14 divided by 2.6390573. Natural log of 3 divided by, natural log of 3 divided by the natural log of 14. I get 0.4162896639. Okay. And here, fingers crossed, because I just made this up on the spot, versus log base 14 of 3. Clean that up a little bit. In fact, I might need more space down here. Versus log base 14 of 3. It is, but I've got the any base on my calculator, right? So if I do log base 14 of 3 on my calculator, and I'll indicate that just by making it this button, right? So on my calculator, I get equals 0.4162896639. Don't worry, they will always be the same. Right? So that's what I mean by, you don't have to have a log base bx button on your calculator, right? We can have a look and see if we can find it. If you don't though, you will have an ln button. And so you'll always be able to just do the natural log of this over the natural log of this, right? To be able to solve these things. So it's never gonna be, this to the power of what equals this, right? We don't have to do that, right? We can just, because what are we asking here, right? 14 to the power of what equals 3? Yuck. No thanks, right? Turns out it's this. We would never get there, right? And so, so we're just gonna use either the change of base formula or your calculator to do these things. You guys are done, huh? You're right, it is a pretty good place to stop. Cool. So have a read through, try the rest of the problems that we've got here. We didn't really talk about the properties of logs, but try at least evaluating those log problems in 4.3. Then we'll pick it up next day. Any questions though before we end? Have a good weekend. Yes.
If the angle is 1, then